We'll do another example now of a partial differential equation boundary value problem in the cylindrical coordinates. Temperature in a plate, in a round plate. Again, we assume radial symmetry so that at any angle, it's the same temperature. Here is the governing partial differential equation, where R is the radius from the center of the plate. Goes from the center of the plate, R equals 0, out to some finite limit. So it's a perfectly circular plate. It's the temperature over time, where time is greater than 0. The boundary condition, or one boundary condition, is that it's insulated at the outer edge. It's going to mean that the derivative of U, which is the temperature in the plate, with respect to R, out at that outer edge is 0. And then there's an initial condition. Time t equals 0, there's a given temperature over the plate. Function of R, radius from the center. So it's radially symmetric. We do the separation of variables again. We'll assume U equals R times T. Those are our two variables, little r and little t. So big R and big T are the functions of those variables. U equals RT. This will be R double prime T. This will be R prime T. This will be RT prime. So here's that equation. Well, here's this equation rewritten in the separated variables. Do some algebra and separate the variables. So we have all R stuff on one side, all T stuff on the other, set them equal to the same separating constant. At least for the T equation, it's this standard first order equation. We have a solution for that. Here it is. And by the way, this K is strictly positive. We're going to apply an implicit boundary condition again, which is boundedness. The temperature can't go off to infinity. Which means R must be bounded and T must be bounded over the range of their variables. For T to be bounded, that means lambda has to be, can't be negative. So it's at least greater than or equal to 0. So we're already starting to eliminate some eigenvalues. So we're limited to positive eigenvalues or non-negative eigenvalues. So now let's look at the R equation. Here's what it was separated. A little algebra. And this again is Bessel equation of order 0. No, it's not. Well, it will when lambda is not equal to 0. First, let's look when lambda equals 0. This part equals to 0, and this is the solution to that equation. It's a certain equation. We would have it on our formula sheet. And because R must be bounded, we have to set big B equal to 0 here. So the solution there for the R function is just a constant. We get that because it's bounded. Let's see. Since it's a constant, its derivative 0 satisfies our boundary condition. So that's okay. So we accept lambda equals 0 as an eigenvalue. Associated eigenfunction is just some constant. Now for positive eigenvalues, positive lambdas, this is you can multiply by R and you'll see that it's a Bessel equation of order 0, which has this general solution. And again, it's got to be bounded. Bessel functions of the second kind are not bounded when the argument goes to 0. And an R of 0 is the middle of our plate. That's included. So we have to set big B equal to 0, and we accept just the Bessel functions of the first kind. Boundedness requires that. So we've got our eigenvalues. We have our eigenvalues here yet. Here's the eigenfunction. Here's the eigenfunction. And okay, its derivative, yes, the derivative of Bessel function of the first kind. And when I plug in out at the edge, I plug in C for R, that has to equal 0. So this is our eigenvalue generating relationship, the derivative of those guys. You'll get an infinite number of crossings. Go back to what the function looks like. Here's J0. You can kind of imagine its derivative. But its derivative will also cross the x-axis an infinite number of times. And every place where it crosses, that generates an eigenvalue. So you put all those together. T's, let's see, for when lambda equals 0, T is just going to be a constant as well. I had that on this chart. It doesn't look like it. When you put it together, for the 0 eigenvalue, you just get 2 constants multiplied. So absorb that into 1 constant here. And then for all the other ones, here's the part of the T. There's the solution to the T part. There's the solution to the R part. And an infinite linear combination of them. Anyway, here's our general solution. Don't know the big A's yet. This eigenvalue generating relationship. The initial condition is that time t equals 0. When I set t equal to 0 up here, this e to the stuff just becomes a 1. So this is our solution at time 0. That is our initial condition, which is some function given to us. This eigenvalue generating relationship. So we need to expand this guy in a Fourier-Bessel series again, but remember how you do that. The form of the Fourier-Bessel series depends on the form of the eigenvalue generating relationship. With this kind of eigenvalue generating relationship, that is case 2. It says, here's how you expand such a guy. Here's the expansion. And here's what those coefficients are. We get that all from Fourier-Bessel series, which we talked about a little bit earlier. We're going to match coefficients. So this big A sub 0 has to equal this little c sub 0. This the big A sub n's are going to equal these little c sub i's. Here's what they are. You do the rest of it. Here's what the big A's are. It gives us a complete solution now. Here's what we had before. Now we have the big A's. By expanding our function in a Fourier-Bessel series.